So now we'll see the biasing of a JFET. What do you mean by biasing? So right now we had seen how FET behaves, and this is what the diagram we had seen. Change in VGS, change in ID, change in VDS. So these are the biasings given or the supply given so that your transistor works. So first thing is that we'll give the symbol for this, and the symbol for the FET looks like this. And normally the arrow is shown at the gate terminal. If it is going inside, that means we call it as a N channel JFET, where if the symbol or in the symbol if arrow goes outside, that means we call this as a P channel JFET. So this symbol N channel symbol represent in this fashion also, and even in P channel they represent in this fashion also. So both the symbols are true whether you are using N channel in this fashion or if you are using P channel either in this or in this fashion, both are true. So this is about the gate everywhere. And second is always drain is shown at the top and source at the bottom. Drain at the top, source at the bottom, drain at the top and a source at the bottom, drain at the top and source at the bottom. So this configuration normally is true. Always remember in JFET or MOSFET or E-type or D-type MOSFETs, your drain is always shown at the top. Remember, in some cases it is shown in the bottom whenever you are going for doing some complementary biasing. That time it will be necessary. That time I'll talk about it. So what do you mean by biasing of JFET? Whatever working we had seen here, the same is represented now by a symbol. So don't get confused. We will be now henceforth using a symbol instead of showing this channel and the terminals and heavy doping of P is not necessary now. So now we'll be only using the symbols. So making the same circuit what we had seen here with the symbol will look like this. So I'll show you the circuit how it will look, and I'll be taking N channel only because you are comfortable with the N channel MOSFET, that's why. So again, drain, source, gate. We are giving biasing here, negative biasing for N channel, and that was VGS voltage between gate to source. This is your gate terminal, this is drain and this is source terminal, and VDS between drain to source, positive to the drain and negative to the source. This is the same working whatever we had seen here. The only thing is that we have replaced a semiconductor diagram with a symbol, and that's why drain, gate and source you can find it here. So now we want to make this to be as an amplifier. That means it should amplify something. And what is that amplifying? We had seen from the transfer characteristics that there is a change in ID current with the change in VGS. That means output quantity changes with the change in input quantity, which is called as a VGS. So ID current, again see what I am saying, ID current only changes by the change in input quantity, which is a voltage or electric field. That's why field effect transistor. So, and that is shown by a Shockley's equation where just now we had seen. If ID current has to change, that change will be because of the change in VGS, whereas IDSS and VP are the constant quantities which are given in the specification sheet. And this is what we need to make this FET as a amplifier. So this is our ID current, this is the VGS voltage. Now this ID current is dependent on VGS voltage. So how we call this as an amplifier? What do you mean by amplifier? Amplifier, that means output voltage is input voltage is amplified to the output voltage. So output you will be getting as an amplified version of a input voltage. So to get that, what we'll do, connect some resistance here. I'll call this resistance as RD because it is connected to drain terminal. So the current flowing in RD is ID. So the voltage across RD, if I want to plot, that will be we'll call this as a output voltage VO, which will be equal to ID into RD. But ID is dependent on input quantity, which is VGS, isn't it? So ID depends on VGS and does not depend on whatever RD you are connected. Let us say we have made ID equal to, say, 2 milliamperes. How we have made this 2 milliamperes? By deciding how much is the value of VGS, and by how we decide the value of VGS from the formula. So whatever, if you want ID to be 5 milliamp or 2 milliamperes, IDSS is given in the specification sheet, normally 4 milliamperes. VP is given in the specification sheet more, and that too minus 4 volt. Remember, VP, if it is minus, you have to put there minus. So these two quantities are fixed, which are coming from the specification sheet. Now you have to find out how much is VGS to get ID is equal to ID of 2 milliamperes. So to get ID of 2 milliamperes, we have to change VGS, and because of that we have done it already. Let us say some ID flowing is 2 milliamperes, and into RD, how much output voltage you want. If I want it to be of 1 volt, then I'll connect this RD of 500 ohms. If I connect it to of 500 ohms, then it will be 2 into 5, 10 millivolts. 10 1000 millivolts. Now removing milli, it will be 1 volt. So I can have 1 volt output voltage by connecting RD of 500 ohms. Now if I want to increase output voltage, okay, how much we want? Let us say we want it to be of 2 volts. No problem, just change RD from 500 ohms to 1 kilo ohms. Then 2 milliamperes into 1 kilo ohm, that will be 2 milliampere into, so VO1, I'll call it as 2 milliamperes into 1 kilo ohms. 1 kilo ohms, that means 1000, and this is 2 into 10 raised to minus 3. So this minus 3 and plus 3 will get cancelled. You will be getting 2 volts as output voltage. So whatever output voltage you want, accordingly you have to change the value of RD rather than doing any other changes in this. So if I want it to be of 10 volts, no problem, again I can change RD and make it of a 10 volts output voltage across this RD. This is why we call this type of amplifiers, just like FET amplifier in our case, and BJT amplifiers which you had studied previously. Output quantities depend on the input quantity and is not at all dependent on whatever resistance you are putting it here. Now you must be confused why this is not happening to this circuit. Let us say simple circuit, a voltage source, a resistance RL, and we are taking output voltage across this RL, VL. Let us say this is V and some current I. So according to this VL, I can write which is equal to I into RL, isn't it? So let us say if V is equal to 2 volts, how much will be VL equal to? VL will be equal to some current flowing in this into the resistance. So but parallelly the voltage is same, so it will remain as 2 volts only. Getting? So if I change V, then VL will change, so almost it will be equal to same V. If I change a resistance, if I change resistance of 10k from previous 1k to 10k, I have shifted, I increased it by 10 times. So if I increase RL and I'm continuing giving 2 volts, then what will be the current? Now current will decrease, but the voltage across VL will remain constant of 2 volts because of Ohm's law, which says V is equal to IR. V is constant, and by changing R, increasing R, I will decrease and your this potential will remain always a constant. So that this is how by simple circuit, this circuit does not increase the output voltage by changing RL, remember, but for this circuit, above circuit, by changing RD, your ID will not change. Here what is happening by changing RL, I is changing because of Ohm's law, which says V is equal to IR. So if I want to calculate I will be equal to V divided by R. If I increase R, I will decrease because this is a constant quantity. If I decrease R, then I will increase because this is a constant quantity V. So your I is proportional to resistance RL in this case, but for this case I is not proportional to RD, but ID depends on input voltage VGS, and that is why we can use this amplifier, you can use this circuit as a amplifier or this device as a amplifier.